Okay, now I'm going to wrap up the module, my module on the extended Kalman filter, which means I'm also wrapping up this whole course called Random Processes and Kalman Filtering. By the way, a reminder, this, once you get to the extended Kalman filter, you're pretty advanced. If you're getting serious into extended Kalman filters, you're probably going to need to consult more than my videos and even more than my website. Um, you know, we're getting into the practicing engineers Kalman filtering. Um, anyway, there's just a couple of things I wanted to say before I totally end everything. Let's go back to the tracking problem again. Let's say I track in 2 dimensions, north and east. So my state vector might be this: position east, velocity east, position to velocity north. My state space, it would look like this. And if that's what I measure, position east and position north, this would be my measurement equation. Everything here is linear. And even better, if your measurement errors were decoupled, meaning whatever you measure, your position east is independent of your measurement error position north. R matrix would be diagonal. And you could actually do this bigger problem in terms of 2 separate little filters, little state space models of only 2 dimensions each. You'll do your, you have your east equation and your north equation would look the same way. And we could use a Kalman filter for that. We don't need an extended Kalman filter for this problem when it's set up like this. Let's talk about bearings only tracking. Here are these dots, us, observer. Here's some vehicle out there in a straight line track. So we know where we are, and we know the bearing from true north, I guess, to the thing we're tracking. So when we're here, we get this bearing. All we know is it's somewhere along this line. When we're here, all we know is it's somewhere along that line, etc. Well, it's nonlinear. Let's see. And we could say, well, it's all nonlinear we could still say the dynamics are linear. The target is following good old linear dynamics. But now our measurement model is nonlinear. Did I say that right? The target itself, the vehicle we're tracking, that's all linear. But our measurements are nonlinear compared to this guy's position. If we know the position east for the target and the position north of the target, we subtract off our own position east and north. And we can calculate what there's a relationship between those things and the bearings. So here's the nonlinear equation for what we measure versus our state variables. Our state variables are position east, position north, and we know our own position. So we have to calculate this capital H matrix by taking these partials, and that's easy enough to do. How did all this work? So we kept linear dynamics, and only the measurement model was nonlinear. So it seems like it's nice and set up for an extended Kalman filter. That worked. It works terrible. People have tried this and it doesn't work hardly at all. filter divergence, it's not just inaccurate, it goes goofy. But you know what did work? Or at least kind of sort of halfway decently worked? A different state model with different state variables. Instead of using position north and position east, you use these kind of weird things. Your bearing rate, range rate over range, that fraction, that ratio, bearing itself in the inverse of range. Nonlinear as heck and very weird state variables, I think. But then you can make the measurement model linear. It was just this. You know, that beta is the thing you measure. So this H is just this nice linear matrix. And that worked okay. The moral of this is once it gets to things that are nonlinear, there's art to it. There's no known way, algorithmic way to come up with your state space model. Where do you put your nonlinearities and what do you try to keep linear? Me and at least another guy that worked on these things somehow thought it's good to keep your measurement model linear or more linear and leave your nonlinearities for your state, your process equation. But anyway, I just want, the whole point of that is there's some art to this when it gets to this level. One last thing is I always ask my students, I think almost every time I taught this, just go online and find any application you can of a Kalman filter or an extended Kalman filter. And this is, I don't even know if it's exhaustive, but these are the kinds of things that someone tried to track using some kind of Kalman filter. Indian stock market, frequency brain neuron firings, soil moisture. I mean, it's all kinds of things that you might not have associated with Kalman filters. It's anything that changes over time, is dynamic. I guess it could even be changes over position. Somehow is dynamic and take measurements of it. Anyway, that ends the module and it ends the course. You got something out of it. Bye-bye.